All right. Up until now, almost everything did in terms of circuit analysis, and it was deterministic. We dealt with deterministic systems. We dealt with, they may be complicated, but they were deterministic. Even when we talked about interference, for example, in the context of differential pairs and things of that sort, you're talking about another source of signal coming in and interfering with you, but that was more or less had a deterministic source. Now, today we will start our discussion of noise in electronic circuits. And then what we'll do, we'll break it up into different pieces. So the first part, we'll talk about the mathematics. First, we'll talk about the mathematics, very simple, quick review of the mathematics of stochastic processes and random processes. Then we'll talk about the physics of noise, what the physical sources, what are the properties of various noise sources. Then we'll talk about circuit models, and then we'll see what the practical implications for circuits are. Now, but you may ask, why are we worried about noise? Why do we need to really even think about noise? What's the point? Well, why do we worry about noise? It's a question to you.
It's something that's always going to show up in a real system.
Correct. It will always show up in the real system. And what would it limit? What is the thing that it will limit? Dynamic range. In other words, the smallest, it determines the lower end of the dynamic range. It determines what's the smallest signal that you can detect before being significantly affected by the noise. So it determines the range, the same way that nonlinearity determines what's the largest range of signals that you can deal with. Now, noise determines the other end of the spectrum. It's like basically the smallest signal that you can actually deal with. So then for noise, we have to think about, basically think about a random process, right? A random process is something that there are many different ways of seeing it. For example, as we'll talk about the physical sources of noise and what happens, but for example, if you take a resistor R, and we'll talk about what happens physically and things of that sort in a short while, but then if you look at the voltage of this thing and you have a very precise amplifier, what you will see is that what comes out is not, even if there's no signal presence, there's some fluctuations in this, right? So you get something that's varying, and it's random, and it's unpredictable. Now, of course, this is because of the random thermal movement of electrons inside the resistor, and we'll talk about the physics of it later. But so if you have something like this, in general, if you have a random process, if you look at the sample of the random process, let's call it x of t, there's no predictability because it's random by itself. So what you can only talk about is the statistical properties of these things, right? You cannot talk about deterministically this thing, because next time you look at this resistor, you will not see the same waveform. You see a completely different waveform. But the statistical properties of these things can be determined, and that's what we will be mostly concerned with and talking about. So in general, the statistical properties do not have to remain constant with time. They can change with time. They can be changing in a periodic fashion, in an aperiodic fashion. All sorts of things can happen. You can have something whose statistical properties can change. And this can happen. We'll talk about it. For example, if this was dependent on some parameter, let's say temperature. Again, we haven't shown any of these things. We will. Then if I start heating this up, then the statistical properties would presumably change with time, right? So they don't have to necessarily stay constant. But now, we are going to understand this thing, we have to understand the concept of an ensemble. So what is an ensemble? So imagine you have a bunch of resistors with exactly the same value. So the values are identical, right? So now if you look at the waveform of each one of them, what would you see? Would you see the same waveform? Not necessarily, right? Probably not. So each one of them will have some random waveform associated with it that would be different if you look at the individual waveforms, although the values of the resistors are the same, right? So if you look at these waveforms, they look different. Now, how can we look at the statistics of these things? For example, if you wanted to look at an average, or in general, the higher order moments that we'll define soon. There are two different ways. So we can let's say we wanted to take an average of this thing as a starting thing. You can take an average over what? So by the way, these are waveforms over time, of course, right? So this is basically time. So you could average two different ways, right? One is that you can say, okay, I'm going to take the voltage of one resistor and average it over time. Or you can do a mean square average or something like that, or other kinds of averages, right? So let's say any kind of statistical property. You can say, okay, I will look at one resistor and look at it across the time, right? So these will be time statistics or time moments or time averages, right? You could, so that would be, let's say, we show it this way. Well, okay, this is horrible. Okay, so this would be a time average. So you can do a time average on this one, you can do a time average on that one, et cetera, right? Or you could say, look, I want to look at the ensemble, a large number of these things. At any moment in time, I want to look at what that statistical properties of all of these things averaged is. So you can see that there are two different kinds of averages you can perform, right? You can average one resistor over time, or you can say I have an ensemble. In essence, this is a thought experiment because you can't have an infinite number, but you have a very large number of these identical resistors and see at any point in time when all the parameters are the same for them, what does the thing look like. So these two averages are in principle not the same, right? They would not necessarily be the same. Now, if indeed they are the same, this is a special kind of process. We call them ergodic processes. So definition of an ergodic process is one in which the time average and the ensemble averages are the same. Now, there's also another terminology, is that if the ensemble average, in general we said it could change with time, but if the ensemble average is always the same at all different times, if it doesn't change with time, we call that process stationary. So there are two things that we talk about, right? So stationary process really is that the time average or the ensemble average doesn't depend on time, not a function of time. It's not a function of time. And then you have ergodicity or ergodic process is where the time average or ensemble average is the same as the time average. So these are two things that are kind of like definition, really, right? Now, if you have a process like this, so what kind of averages can we define? You can have, of course, so how would you define the time average, let's say, if you wanted to define a time average? How do we define the time average? If you had a periodic signal, how do we define its time average? Integrate over a period and divide it by the period, right? So for example, if you had x of t, if it was a periodic signal, then you would integrate it over the period and divide it by the period, right? So that would be what you would get, the kind of average you would get for a periodic signal, right? Now, how do we deal with an aperiodic signal if it's not periodic? This is obviously, or clear, apparently it is not periodic, right? Right. So this is one of the classic tricks, right? If you know what to do with something that's periodic, and if you want to deal with something aperiodic, assume that the period is infinity. Right? So then basically, in that case, you're saying that take this limit, and that would be your average of x. And similarly, you can define something that's called the so-called power of the signal, right? So if, for example, if this was the voltage, if you were looking at actual voltages, the power of the signal, obviously the instantaneous power is what? Is v squared over r, right? If you drop it into some sort of resistor. And then what you have is that then you're integrating that from negative infinity really to plus infinity, or you can write it this way. dt, so this is v of t. And now you get the power, right? You get, this is basically the power that's delivered. Now, in general, if X is some sort of a voltage or current, in general, we show it as a signal. So if, for example, X was in voltage, then you could actually write this thing as the power, as the statistical average of X squared, or V squared, over R. So what this means is that you can actually define these higher order moments. Like, for example, let's say this, if you want to define it in general, if you had a signal of X form X squared, you could define it similarly, its power, so quote unquote power, as the average of its square, right? So this would be its power. So now if this X was a voltage squared, then you divide it by R. If it was a current squared, then to get the actual physical power, then you would need to, for example, do an R times I squared, right? If it was going to a resistor. Yes? Yes, I did forget 1 over T. Thank you. Yes, thank you. So these are basically the kind of like averages that we define, right? We are assuming that it's infinite period, and we calculate the average. Now, the average, so this kind of average shows a power, right? But it is not very, it's not particularly more informative. It's just a number, right? It just gives you a number. So let's say you look at this volt, the thing, if you actually calculate the power this way, it says the average power of this thing is, I don't know, 1 watt, or 1 nanowatt, or what have you, right? But it doesn't tell you about, there are lots of different things that look completely different that could have that 1 nanowatt, right? So for example, this waveform may give you 1 nanowatt, this waveform may give you 1 nanowatt. But they look very different. They behave very differently, right? So the question is that, can we get more information? Is there a way for us to think about the averages to get more information? Now, one of the things to do this thing, there are 2 ways to do this, right? I mean, there are many different ways to do this, but 2 main ways of doing things, as in general, is in time and frequency, right? So now we'll define power spectral density. So the definition of power spectral density is what we're going to define now. And then we'll show how it relates to the time property. So power spectral density is a frequency domain measure, right? So what is power spectral density? So let's say you have a source, right? You have a signal, some x of t. So x of t is going into the system. So this is one of those little waveforms, right? And it's going into, so we have this coming out, or it could be a voltage, it could be a current, but in general, let's say x of t. The idea here is that you actually, if you pass it through a filter, so we are talking about the power spectral density. If you pass it through a filter, right, that's a perfect filter. So this is versus frequency. So this filter is centered around f0, or whatever, f1, or f in general, right? Let's call it just f. And it has a bandwidth, let's say delta f. And then take what comes out and put it into a power detector. It could be, for example, one way to make this power detector, it could be a very sensitive thermometer, right? You can actually dump it into a resistor and measure the increase in the temperature of this resistor. And some of the most precise measurements are actually done this way, believe it or not. So it's a bolometer, for example, is something like that, would do something like this. Now, if you take this and dump it into a power detector and then start moving this filter to different frequencies and doing different measurements, what would you see? So you will get a plot, right, versus frequency. Now, as long as you make this, so if you start with something large, a large bandwidth, then you will have things that are, so you get a number here, number here, number here, number here, number there, right? Versus frequency. You get data points. Now, if you want to get a finer and finer resolution of this thing, what do you need to do?
Shrink delta f.
Shrink delta f, right? Shrink the bandwidth. Now, if you shrink the bandwidth, would you get more or less power in general from? you get less because there's less of the energy that's going through. So if you just shrink it and plot what you measure, you will get something that's here, 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 here. And as you shrink delta F, this is going to become smaller and smaller, right? So that's not a good way of doing it because you ideally want to get a continuum, right? You want to get a continuous curve that describes you the density of the power, how much energy is exactly at which frequency, which basically means that delta F needs to go to 0 in the limit. Now, if you just take delta F to 0, really, you're going to get 0 power. So what you need to do is to normalize it, right? So you can say, OK, what I'm going to measure is going to be Px at delta F normalized by delta F. And then in the limit, really want delta F to go to 0. But if it makes you feel better, just imagine that you have, let's say, if 1 hertz is sufficiently small bandwidth for your application, you can say, well, I take a 1 hertz filter here, 1 hertz, and move it around. But in reality, you're taking something that's infinitesimal and moving it around because that allows you to deal with things that are sub-hertz and all those things. But what will come out will have units of whatever x units are per hertz, right? And that would be a continuum because if you do this, then it allows you to calculate the so-called power spectral density, which will show you as S sub x of f. So it's a function of frequency. So this is basically what we're plotting here. S sub x of f. And it will have a shape versus frequency. And what this shape tells you is how much power or how much energy exists in each one of these, or how much power you get for a narrow bandwidth at each frequency. This gives you a sense, gives you a lot more information than just the regular average, right? Because it gives you information about the frequency distribution of this thing. So now, if x of t, for example, was a voltage, then the units of this thing would become volts squared per hertz, right? For V. Or if it was a current, then you get amps squared per hertz. Or if it was some other arbitrary quantity, you get whatever. Like let's say unitless quantity, you get something like 1 over hertz, units of seconds, right? So this power spectral density, and this is, by the way, just let me emphasize this, this is the definition of power spectral density. The relationship with autocorrelation, which we'll talk about in a minute, can be directly derived from this definition. So it's different. I mean, so that's not the definition. This is the definition. This makes sense, right? I mean, you measure the power in every single bit of spectrum, and a bit of the frequency, and then you measure. Now, you can get different kinds of spectra, all sorts of the spectra, and we'll talk about all sorts of spectra and what happens to them. So one classic example of what you can get is the so-called white noise, which basically means that your power spectral density is constant. So that's called white noise. Now, and we will talk a lot about white noise, but before we talk a lot about white noise, from a physical standpoint, do you think this actually can exist? Is it a realist? Is it something that is practical? Do you see any problem with that? Well, let's talk about something before we get to answer that question. So one question is, so the key question is, if I wanted to determine, if you wanted to know what is the energy between two different frequencies, right? How do we calculate it if you have the power spectral density? We said if we wanted to know the energy confined between F1 and F2. So let's say somehow we can put an ideal filter that passes the frequencies between these two and blocks everything else. It's clear that only the energy that's going in, it's confined between these frequencies will go through, right? And what is the amount of that energy? Well, this is the density function, right? So this is very simple from almost by definition. It would be the integral of this thing from F1 to F2 is the power between F1 and F2. Right? Now, obviously, so if this is true, then let's think back about the question about the white noise. What is the power in the white noise? Is the integral of a constant from 0 to infinity, which is infinity. It doesn't converge, right? So it's clear that the real white noise cannot exist. True white noise cannot exist, because then it will have infinite power. It will have more power than there is in the universe. well, there's not power in the universe, there's energy in the universe. But anyway, yeah, you know what I mean. Okay, so that's the frequency domain picture of this thing, right? But now, how about, so that's what, for example, differentiates. You remember I drew two pictures. Let me just maybe redraw them here. So let's say we had a waveform that was like this, and a waveform that looks like this. And they're both random, but you can see that they're different. Now, from a frequency domain perspective, you can imagine that one of them will have more high frequency power content, and one of them will have more low frequency power content, right? Which was completely lost if you did some sort of a regular averaging, right? Well, like what we did with the average power. So, you remember the average power, we defined it this way. Now, the question is that, is there a way for us to kind of generalize this definition of the average power? So we define the average power as, so let me rewrite this here, as the limit of the integral, or, yeah, let me write it as this way, negative infinity to infinity, but it has to be, that's the proper way of writing it for scaling, the way we wrote it before. X squared of t dt, right? But now, if we think about this and say, okay, can we modify this definition in such a way that it captures this frequency-dependent behavior? How can we do a purely time domain thing to capture that information? Is there something that you can tell? You know, look, eyeballing it, right? You can tell that one of them is a more higher frequency than the other one, right? There's something that allows you to do that in these shapes. If I ask you which one is higher frequency, which one is lower frequency, which one has more high frequency content, you would say the red one. But how are you doing that? What are you looking at when you're doing that visually? Yes?
I mean, just naming the level of detail.
Level of detail. Or, yeah, that's good, Dave. Same thing. How much fluctuation there is, right? The level of details. So is there a way we can actually capture that in a definition? Or some definition that will capture that? Now, think about it. If I shift this guy a little bit and compare it with itself, the change is not going to be very large. But if I change this a little bit and compare it with itself, the change is going to be more. So now, if you think about this, if instead of multiplying the signal by itself, we multiply it by a shifted version of itself, then it allows us to do this kind of comparison. Because how much it changes with how much shift would be a measure of how wiggly it is. It's a measure of wiggliness, right? You can call it, right? So now instead, so if we say, let's look at, I can write it this way. Let's write it this way. The limit of t going to infinity of negative t over 2 to t over 2, basically the integral from negative infinity to positive infinity of x of t and x of t plus tau dt. Right? So this is a different quantity. By the way, we can also sometimes show this as like expected value if it's a ergodic process of x squared, right? So this is what we show it sometimes. There are different notation. There's the bra and cat notation, like you can put it in a bracket notation, things of that. So there are different ways of showing different things. But anyway, we'll show it this way. Now, if you look at this quantity subsumes that quantity, right? Because if you set tau to 0, it would reduce to that average. So this new quantity is what we call the autocorrelation function. It's only a function of tau. Well, it's only a function of tau if the signal is stationary. Because if it's not stationary, this relationship would depend on when you do it and how you do it. Yeah, I'm sorry. Actually, I misspoke. So basically, this one is fine. Yeah, now this is good the way it is because it goes from negative infinity to positive infinity. So anyway, so this is the autocorrelation function, right? We show it as Rxx of tau to emphasize that it's x and x being correlated. It's being correlated with itself, and it's a function of tau. Now, if you set tau to 0, what does it give you? It gives you the average power, right? X squared is going to be Rxx of 0, as you can see, right? You set tau to 0, that reduces to that other integral. So that's but this function, now is a function, this is a function, this is not a constant like this before. So this gives you a sense of how things look like. So for example, if I showed you two autocorrelation functions, let's say two new colors. So if I showed you one autocorrelation function that looked like this, and another autocorrelation function that looked like this, which one do you think would correspond to the red one, and which one would correspond to the purple one? So this is basically, these are the time domain spectra. So this is like x of t and x of t. So this is what we're talking about here is the autocorrelation function. And then we can some sort of imagine some sort of a power spectral density for them too. So which one do you think, the orange one or the green one, would be corresponding to the red curve? Orange? So you think or the green or the orange? Green, right? Because if you think about it, there's fast enough fluctuations so that after within a short shift, they lose their correlation. They're not related to each other. It has a completely different waveform now when it's shifted a little bit, right? And that's a measure of the wiggliness. But here, it takes it longer. It takes a larger phase shift or time shift to get out completely uncorrelated, right? So this has a wider autocorrelation, and this has a narrower autocorrelation, right? Now, for a stationary signal, of course, autocorrelation is defined this way. Now, one of the things to keep in mind is that, now, so this is the key result. This can be proven. We're not going to prove it here, but this can be actually mathematically proven that the power spectral, so this is an important result. The power spectral density of the signal x is indeed the Fourier transform of the autocorrelation function, which you can express just the definition of the Fourier transform j 2 pi f tau d tau. Right? So this result can be proven. You can prove this, that this definition of power spectral density would result in a power spectral density that's the exactly Fourier transform of the autocorrelation function. So from looking at that then, so you have two waveforms, two autocorrelation functions that I drew, like, I don't know, I can make it simplified, make them look like this. I don't know. So if you look at these two and look at their Fourier transform, which one do you think would be wider, which one would be narrower? Well, we know what's narrow in one domain, it becomes wider in the other domain, and vice versa, right? So if this is your time domain, then the frequency domain of this thing would be narrower, so it would be a narrower spectrum. If you look at it one-sided, or you can sometimes look at it two-sided, but if you look at it one-sided, so it will have a narrow spectrum. And this guy will have a broader spectrum. So these two are very related. It's a time domain and frequency domain picture of the same thing, because correlation is another way, or autocorrelation, because you're correlating the signal with itself, is a measure of how much signal you basically get at what frequency, because it's a measure of how wiggly it is, or how quickly it changes. Right? So this is important. So now there's one more important, very important piece of, there are a few more important results, but one more thing that we're going to talk about in this exact context. Now, and before we do that, also remember, from this definition, you can easily see that you can also generalize it to two signals, right? Because if you take one signal as x and another signal that's y, then that would be defined as the cross correlation. So just a little side note with what cross correlation, and we'll see cross correlation later too. But Okay, so if this is the picture, then the question is, the very important question is, really, if you have an LTI system, I mean, we are going back to our very classical, often repeated box picture. You have an x of t and a y of t comes out. X of t input and y of t. And let's say this is LTI, linear time invariant. Now, if you have something like this, now, how do we characterize it? In time domain, we can characterize it with the impulse response, right? In frequency domain, the Laplace transform of this thing would give you h of s in the complex frequency. And if you wanted to really look at it only for purely imaginary frequencies, namely sines and cosines, then you get the Fourier transform, which would be h of j omega. If you replace s with j omega, you're looking at it only on the j omega axis. Or if you look at it versus f, you can write it as h of j2 pi f, or simply you can write it as h of f. Because in general, the h of f itself is a complex quantity, although f is a real quantity that goes from negative infinity to positive infinity. Right? So the question is that if you have a system like this, what is the relationship between the what if we know, for example, the autocorrelation function of the input, or the power spectral density of the input? What can you say about the autocorrelation function of the output? Or similarly about the power spectral density of the output? Because this would be very key. Because what will happen is that if you know that you have a certain kind of signal source and a noise, for example, that goes into the system, an LTI system, this allows you to find the evolution of that thing. Yes? Sx of f, yes, yes, thank you. Yeah, this is a typo. Yeah, well, an error. I'm not typing for this to be a typo, so. But anyway, yeah, correct, thank you. So that's in time domain and frequency domain. So this is Sx of f. That's a function of frequency. So now, one of the things, so this is the key question, right? Because if we know this, then we can say if there's a simple relationship we can define between the power spectral density of the output and the power spectral density of the input, or the autocorrelation of the output versus the autocorrelation of the input, and the response of the LTI system, then all of the analysis that we've done for calculation of the circuits and or other things that we've used to determine the transfer functions and all those things, all of these techniques can be useful. Because now we can use them to know what the evolution of the noise would be from the input to the output. And the relationship is actually pretty simple and straightforward. And it's actually pretty, so we can start with the relationship for the autocorrelation function. Now, this relationship, I'll tell you how to derive it. It says basically Ryy of tau is Rxx of tau convolved with h of tau convolved with h of negative tau. And all you need to do to calculate this thing is to basically use this definition of autocorrelation function for y and write y as the convolution of as x convolved with h of t, because this is what y is, right? Y, the way you determine it, is that x of t convolved with h of t. And conversely, like y of s is going to be x of s times h of s. Right? So that's true for deterministic signals. Now for random signals, this is what you get. The way you do it, basically, you will get three nested integrals, one for autocorrelation function and one for each of the convolutions that you get for y of t. And then you need to reorder the order of the integration. You basically just switch the order of integrations, and then you can simplify it, and then you will easily see that this comes out. It's a little bit messy in terms of calculation, but it's not very profound. So now, if this is true, then what can we say about the power spectral density, PSDs? Because this is the relationship in time domain. It says, look, if you know your input autocorrelation function, convolve it with the impulse response, and the impulse response flipped in time, h of negative tau. So convolve it twice, once with h of tau and once with h of negative tau, or h of tau, yeah. But how about if you know this? What is the power spectral density? Well, we know the power spectral density is the Fourier transform of this thing, right? So if I take a Fourier transform of this side and Fourier transform of this side, I should get the answer. So what is the Fourier transform of two things convolved? It's their product. So basically it means that it would be the Fourier transform of this guy, which is basically Sy of f, is Sx of f, then Fourier transform of this thing times Fourier transform of this thing. Well, the Fourier transform of this thing, we know what it is. The Fourier transform of the impulse response is simply just h of s, or h of j omega, right? What is the Fourier transform of h of negative tau?
Same thing for a real system.
For a real system, it's the same thing, but, well, for a real system. But remember, the Fourier transform, the h of j, h itself is complex. Even if h, lowercase h, the impulse response can be real, but capital H can be complex, right? Because it's a Fourier transform, right? This is a complex quantity. So if you look at it, it's very simple to see. Basically what happens is that the sign here flips, which basically means that it becomes a complex conjugate. So the Fourier transform of this guy, oh, well, maybe my color code is broken now. Okay, so Sy of f is Sx of f. So Fourier transform of this thing is h of s, but the Fourier transform of this thing is h star of s, the conjugate. But what is h conjugate times h? Magnitude squared, right? So what you get is simply this times h of f magnitude squared. And this is a key result, because it says, look, whatever power spectral density you have at the input will get multiplied by the transfer function magnitude squared. So essentially, the transfer function shapes the noise. So for example, if your input was a white noise source, let's say, right? So this is Sx of f. And then your system, the transfer function of the system, h of f, was some filter, let's say some bandpass filter between f1 and f2, with some shape, not a perfect filter, right? Then your noise, so this is noise, right? Your output noise is going to be shaped by this magnitude squared, so your output noise will have a shape like this, so you will have noise here. In fact, actually, sometimes you can measure the transfer function of the system by applying noise to it and looking at the shape of what comes out, the spectral density of what comes out. And you may say, why would I do that? Well, sometimes the good thing about noise is that it's, especially if it's like something like a white noise or broadband noise, it's everywhere. So if there are, for example, let's say some parasitic resonance response, right? So let's say there is some peaking here. You may not see it if it's very narrow band or something like that on a sweep, but the noise will make it come out. So you will see it everywhere. And in fact, you can think about doing this in time domain, and some of these things are actually ways of doing system identification. You can actually define a channel or a system based on its response to noise. So that will tell you a fair amount about what kind of system you have. So that's basically the basic properties of power spectral density and the relationship with the transfer function. But this is very important in what you're trying to determine. Now, the other question is that what if you have multiple noise sources? What if you have more than one noise source? How do we deal with them? So again, from a mathematical standpoint. So one of the things we need to think about is, so what we're trying to think about is that you have an x1 of t and x2 of t, two waveforms, let's say. And then you come and, for example, let's say you add them. So you produce x1 of t plus x2 of t. And the question is that, what can you say about the power spectral density of the output? Well, let's start with looking at the average, the regular average first. What is the regular average? So let's call this y of t, right? So y of t, so the average of y is going to be defined as that integral again, of x1 plus x2 squared dt. So now you can clearly see that this gives you 3 parts, right? So you get, I'm going to show the integral just basically from as negative infinity to positive infinity. You get the x1 squared part. You get the x2 squared part. And then you get 2 x1, x2 squared, right? Like the product part. So what is this first one? This is really the power of x1. So this is the power of the output. And this second one is the power of x2 by itself. And the third term, which we show logically this way, this is shorthand notation for that integral essentially, is some sort of a cross correlation or cross power. Because this really depends. This is some sort of a cross correlation between x1 and x2 evaluated at tau equals 0, right? It's a measure of how they're correlated. If you take them and multiply them at all times, is it going to average to something big, or is it going to be just, if they're both completely random, is it going to average to 0? So if they are related to each other, then this can be non-zero. So you have correlated signals. And if you don't have them related, it will just basically, on a large average, it would basically average out to 0. Now to see this, there's kind of like a practical experiment we are going to run. But for this to work, everyone needs to participate. Okay? So you need to participate. If otherwise, it won't work. So we're going to try 2 different things. Think of your favorite 1-digit number. Okay? So you have a favorite number, probably. A single-digit number. And on the count of 3, say it out loud. Okay? I'm going to count to 3, and you say it out loud. But everyone needs to participate. Okay? 1, 2, 3. 1. Okay. All right. That's uncorrelated. Now, why don't everyone use a number I pick? Let's say you say 7. Okay? So on the count of 3, now everyone says that same number. 1, 2, 3.
7.
Okay, that's correlated. Now, when you have correlation, you have more power. Right? Coherence is the same concept. So what happens is that if the correlation was 0, the output power, so no correlation, when you have no correlation, the output power is essentially sum of the individual powers of the 2 sources. Right? So it's just this power and that power, just the powers add. So let's say, assuming that they have the same power, then it would be, so this is assuming that they have same power, then you will get 2x squared, right? But now, assume that they are fully correlated. We'll talk about what fully correlated. Now, in that case, this one and that one are the same. And this basically, if they're fully correlated and have the same power, it means that they are essentially the same. If there are two things that are fully correlated and have the same power. So then what you will get is that you will get 4 times the power. So another way of saying this is that uncorrelated signals add in power, and fully correlated signals add in amplitude. Because if you had an amplitude, and if you took the same amplitude and added it to another one of its same amplitude, you will get twice the amplitude, which means that you get 4 times the power. Because power is amplitude squared. Right? And now, in practice, you may have things in between that are partially correlated. So the correlated part behaves one way, and the uncorrelated part behaves a different way. So this is interesting. So to just a sense of what full correlation means, that full correlation means that 2 waveforms that are related to each other within a scalar. So 2 waveforms that look the same, one of them is larger than the other one, or one of them is exactly the flipped version of the other one if that scalar is negative, or something like that, for it to be fully correlated, 100% correlated. Now, in general, 2 signals can be partially correlated, and if they are partially correlated, there's this thing that you can define as a correlation factor, the ratio of the correlate to the total power that you can have. Now, what causes correlated sources? So this is an interesting thing. This goes really to physics of it, and we'll talk about physics of it later. But in general, if you have, for example, two resistors generating noise, right? The physical phenomenon the physical phenomenon is the same, but the physical properties of the electrons that are generating noise in one resistor is not really normally, under normal circumstances, related. Their behavior is not affected by the electrons moving in the other one, right? So each one of them have independent operations, independent movements. And as a result, what happens is that they are generated by in different physical locations by different physical groups of things. I mean, they may be the same phenomena, but different physical behavior. So they will be uncorrelated if you take two resistors by that argument. Now, when would you get correlated noise is basically when the same source of physical activity leads to different noise sources. So for example, the movement of electrons in the channel of a transistor may be modeled as two different noise sources in different places to capture it. But then there will be, these two sources will have to be correlated, or at least partially correlated. And we'll see those examples. Let me talk about it. So you have to really think about the physical source of the noise and see if those sources, in physical systems, if those physical sources are related to each other or not. And if so, how? Now, there's one last thing I want to talk about, which is this concept of noise bandwidth. So let's go back here. And in general, let's say you have power spectral density like the one that we had. The question is is there a way to define an equivalent bandwidth for this thing? Well, there are different ways to define it. But one of the things is that if you look at the peak and you say, if I wanted to have some sort of really a brick wall equivalent of how much noise is under this black curve, what would that look like? And you may say, okay, well, if I have a bandwidth of this much, the area under this thing is going to be the same as the area under the black curve. We define that as the equivalent noise bandwidth. And what you can do, you can basically say, I will integrate the original power spectral density from 0 to infinity. And you can say you want to equate it to the S max times the noise bandwidth, the bandwidth for noise. Right? So you want this is the area of the rectangle. This is the area of the black curve, under the black curve. And you're equating them, and obviously you can see the noise bandwidth is going to be this divided by that. Right? So you can define it that way. And that's basically the brick wall bandwidth, sometimes called, for noise. So sometimes do that. So this is a very quick review of the mathematical tools that you need, the minimum mathematical tools that you need for analyzing noise electronic circuits. Okay? Any questions?